There is a room in the Elgin National Watch Company factory in Elgin, Illinois, that most people who worked there in 1943 were not allowed to enter. The door was unmarked. The windows were blacked out. Armed guards stood at each end of the corridor. Inside, under lights so bright they gave the workers headaches, women sat at benches and assembled devices that looked nothing like wristwatches. The devices were cylindrical, about the size of a man's fist, packed with components so small that the assemblers worked with tweezers and magnifying loops strapped to their foreheads. Each device contained a tiny radio transmitter, a tiny radio receiver, a battery, an amplifier circuit built from miniature vacuum tubes the size of a woman's thumbnail, and a detonator. When finished, the device was inserted into the nose of an artillery shell. The room smelled of solder flux and machine oil. The air was filtered because dust, any dust, even a particle smaller than a grain of pollen, could ruin a component. The benches were wood, worn smooth by elbows and forearms. The tools were arranged with a watchmaker's precision, each tweezers in its slot, each screwdriver in its holder, each loop hanging from its hook. The women wore cotton smocks with no pockets because pockets could catch and bend the tiny wires they handled. Their hair was tied back or covered. Their fingernails were trimmed short. Some of them had spent years making watches. Some had come from jewelry shops. A few had been recruited from beauty parlors because the fine motor control required to shape a fingernail was, it turned out, almost identical to the fine motor control required to seat a miniature vacuum tube in a socket the size of a pencil eraser. The women did not know what they were building. They had been told it was a special component for the war effort. They had been told not to discuss their work with anyone, including their husbands, their mothers, their priests. They had signed documents that invoked penalties for disclosure that they did not fully understand, but that sounded severe enough to ensure compliance. What they knew was that the work required the steadiest hands in America, and that the company had recruited them specifically because they had spent years assembling watch movements, seating jewel bearings, adjusting hairsprings, fitting gears with teeth smaller than the point of a sewing needle. They were building the VT proximity fuse, the third most important secret weapon of the Second World War, after the atomic bomb and radar. But this story is not about the proximity fuse specifically. It is about something larger. It is about the moment when the United States of America discovered that the skills needed to win a modern war were not the skills of blacksmiths and ironworkers. They were the skills of watchmakers. In 1940, the United States military had a problem that it did not fully understand. The problem was not a shortage of steel. It was not a shortage of men. It was not a shortage of factories. The problem was a shortage of hands that could work to tolerances measured in 10,000ths of an inch. Modern war demanded precision, not the approximate precision of a horseshoe or a railroad spike, but the absolute unforgiving precision of instruments, bomb sights, gun directors, fire control computers, rangefinders, altimeters, gyroscopes, timing mechanisms, proximity fuses. These devices contained gears, cams, bearings, shafts, springs, and levers machined to tolerances that were, in many cases, tighter than anything the mass production industries of America had ever attempted. A gear in a Norden bomb sight had to mesh with its partner within a fraction of 1,000ths of an inch. A bearing in a gyroscope had to be round to within millionths. A hairspring in a timing fuse had to oscillate at a frequency precise enough that the shell would detonate within feet of its intended burst point after being fired from a gun at 20,000 Gs of acceleration. The automobile industry could not do this. Ford could stamp fenders. General Motors could cast engine blocks. Chrysler could machine crankshafts, but none of them could cut a gear with 60 teeth on a wheel the size of a dime to a tolerance that would allow it to mesh with a pinion the size of a grain of rice and do it 30 million times without error. The skills required were not the skills of the assembly line. They were the skills of the jeweler's bench, the watchmaker's loop, the instrument maker's lathe. They were the skills of an industry that most Americans considered a quaint anachronism, the American watch industry. And that industry was, in 1940, still alive. Barely. The American watch industry had been one of the great precision manufacturing achievements of the 19th century, and almost nobody outside the industry appreciated what that meant. The Waltham Watch Company, founded in Massachusetts in 1850, had pioneered something that sounded simple but was, in practice, revolutionary: the factory production of watches with interchangeable parts. Before Waltham, a watch was a bespoke instrument. A watchmaker in London or Geneva hand-fitted every gear, every spring, every pivot to the specific case and movement he was building. If a gear broke, the owner had to return the watch to the same watchmaker because no other gear would fit. Waltham changed this. Waltham made gears that were identical, cut on machines, to specifications, with tolerances tight enough that a gear from one watch could replace a gear from another. This was the American system of manufacturing applied to the smallest, most precise mechanisms in existence, and it made the United States, for a time, the world's leading producer of precision timepieces. The Elgin National Watch Company, founded in Illinois in 1864, grew into the largest watch manufacturing complex on Earth. At its peak, the Elgin factory employed thousands of workers and occupied multiple buildings spread across the town that bore the company's name. The factory made everything, from the raw brass plate stock to the finished, cased, timed, and regulated watch. They drew their own wire. They cut their own screws on automatic screw machines that could produce 100 screws per minute, each one identical to the last, each one threaded to a pitch measured in thousandths of an inch. They drilled their own jewel bearings from synthetic ruby and sapphire, using diamond-tipped tools that cut the hardest materials on Earth with a delicacy that seemed impossible for industrial machinery. The Hamilton Watch Company of Lancaster, Pennsylvania, built railroad chronometers so accurate that they became the standard of the American transportation system. A railroad chronometer had to maintain accuracy to within 30 seconds per week, a requirement imposed after a train collision in 1891 at Kipton, Ohio, caused by an engineer whose watch had lost 4 minutes. The tragedy led to the adoption of strict timekeeping standards for all railroad personnel, and the companies that met those standards, Hamilton, Waltham, Elgin, Illinois Watch Company, became the backbone of American precision manufacturing. Bulova, founded in New York in 1875, built a reputation for innovation that would later lead to the first electronic watch. Joseph Bulova was a Czech immigrant who understood that the American market wanted precision at a price. His company produced watches that were affordable without being cheap, reliable without being extravagant. The Bulova factory was a model of efficient precision manufacturing, not the bespoke hand-fitted tradition of the Swiss, but the American tradition of precision through standardization, quality through repetition, consistency through measurement. These companies were not mere assemblers. They were complete precision manufacturing ecosystems. They made their own gears, their own springs, their own jeweled bearings. They cut their own screws, ground their own pivots, polished their own plates. They heat-treated their own steel, mixed their own alloys, and formulated their own lubricants. The workers who assembled a watch movement handled parts so small that some could only be picked up with a moistened fingertip or the sharpened end of a pegwood stick. They worked under magnification in rooms where the temperature and humidity were controlled because thermal expansion could change a tolerance by enough to ruin a finished movement. Their hands had been trained for years to perform operations that were invisible to the unaided eye. A watch movement contains between 100 and 300 parts depending on complexity. The escape wheel, the heart of the timekeeping mechanism, has teeth so fine that a human hair laid across them would bridge 3 or 4. The balance wheel oscillates 5 times per second with a precision that gains or loses no more than 30 seconds per day. The mainspring stores energy for 30 to 56 hours. Every surface that touches another surface is polished to a mirror finish to reduce friction. Every bearing is a synthetic jewel, ruby or sapphire, drilled and countersunk to a tolerance of a few 10,000ths of an inch. This was the precision that America needed in 1940, and the only people who possessed it were the men and women who made watches. When the war came, the watch companies stopped making watches. All of them. Completely. Elgin halted civilian production and converted its entire factory to military work. Hamilton did the same. Waltham, Belova, all of them. The assembly lines that had produced pocket watches and wristwatches for the American consumer were retooled to produce the instruments of war. The workers who had assembled watch movements now assembled bomb fuses, aircraft altimeters, naval chronometers, gun sighting mechanisms, and sapphire jewel bearings used in the elevation and traverse mechanisms of cannon. The scale of the conversion was staggering. Elgin alone produced military watches, chronometers for the U.S. Navy, fuses for artillery shells, altimeters and instruments for aircraft, and sapphire bearings for cannon aiming systems. The company was awarded 10 Army-Navy E awards for fulfilling contracts ahead of schedule. Hamilton produced over 1 million marine chronometers and military watches. Belova built precision timing mechanisms for bomb fuses and navigation instruments. But the watches themselves were only the beginning. The military's real need was not for watches, it was for the skills that watchmaking had developed. The ability to cut, grind, polish, assemble, and inspect parts measured in thousandths and 10,000ths of an inch at production volumes that the traditional instrument-making industry could never achieve. Consider the Norden bomb sight. Each one contained over 2,000 precision parts. Gears, cams, differentials, gyroscopes, mirror assemblies machined to tolerances that were unheard of in mass production before the war. Nearly 90,000 were built at a total program cost exceeding $1 billion. The gears inside those bomb sights were not stamped, they were cut, one tooth at a time, on gear hobbing machines operated by workers whose hands had been trained in the watch factories and instrument shops of the American Northeast. Consider the fire control computers that aimed the guns on every major warship and every B-29 bomber. These were mechanical analog computers, collections of gears, cams, differentials, and resolvers that performed trigonometric calculations in real time. The Singer Manufacturing Company, the sewing machine maker, built over 20,000 of them for the B-29's central fire control system. Singer could build them because sewing machines, like watches, require precision gear trains, cam mechanisms, and tight tolerances. The Singer factory in Elizabethport, New Jersey, went from making machines that stitched fabric to making machines that aimed machine guns. And the transition was possible because the underlying skills were identical. Consider the proximity fuse. 22 million were produced during the war at a cost of approximately $1 billion. Each one contained miniature vacuum tubes, tiny glass envelopes smaller than a woman's thumb, containing filaments, grids, and plates assembled under magnification by workers whose dexterity had been developed in the watch and electronics industries. Sylvania Electric produced over 5 million of these tubes at its factory in Ipswich, Massachusetts, staffed largely by women recruited from the local community and trained to perform assembly operations that required the hand-eye coordination of a watchmaker and the patience of a saint. The vacuum tubes inside each proximity fuse had to survive being fired from a gun. The acceleration at the muzzle was 20,000 Gs, 20,000 times the force of gravity, applied instantaneously. At the same time, the shell was spinning at 25,000 revolutions per minute from the rifling. Every solder joint, Every wire connection, every glass seal, every filament mounting inside those tiny tubes had to withstand forces that would crush most electronic components into dust. The fact that they worked, that 52% of them worked on the very first test, and eventually over 90% worked in production, was a tribute to the precision manufacturing culture that the American watch and instrument industries had built over the previous century. The workers who performed this precision assembly were overwhelmingly women. This was not an accident. It was not a concession to the labor shortage, though the shortage was real. It was a recognition that the specific physical skills required, fine motor control, patience with repetitive precision tasks, the ability to work for hours under magnification without fatigue, were skills that women possessed in abundance and that the watch, jewelry, and beauty industries had already trained. Watch companies had employed women for decades. The delicate work of fitting jewel bearings, adjusting balance wheels, and testing escapements had always been performed primarily by female workers. When the military contracts arrived, the companies knew exactly where to find their assemblers. They recruited from their own workforces, from jewelry shops, from beauty parlors, from any trade that required a steady hand and a tolerance for performing the same tiny operation 1,000 times a day. At the Sylvania plant in Ipswich, Massachusetts, where the miniature vacuum tubes for the proximity fuse were assembled, the workforce was almost entirely female. The women soldered connections under magnification, sealed glass envelopes with precision torches, and tested finished tubes on circuits that measured electrical performance to fractions of a milliamp. The work was tedious, demanding, and dangerous. The materials included beryllium, a metal that could cause fatal lung disease if inhaled as dust. Some of the women who worked at Sylvania during the war later developed malignant mesothelioma and other respiratory illnesses. They had been told they were helping win the war. They had not been told they were handling materials that might kill them decades later. At the Elgin factory in Illinois, women who had spent years adjusting hairsprings now calibrated the timing mechanisms of artillery fuses. The skills were identical. Both required the ability to manipulate a spring-loaded mechanism until it oscillated at precisely the correct frequency. The difference was that a watch hairspring controlled the accuracy of a timepiece. An artillery fuse hairspring controlled when a shell exploded. A watch that ran 30 seconds fast was a minor annoyance. A fuse that detonated 30 seconds late was a weapon that missed its target by miles. The women understood this. They did not need to be told what was at stake. They could calculate in the simple arithmetic of wartime that every fuse they assembled correctly was a shell that might save a soldier's life. Every fuse they assembled incorrectly was a shell that might fall short or long or fail to detonate at all. The reject rates were tracked, the inspectors were rigorous, and the women, working 10 and 12-hour shifts under lights that made their eyes ache, achieved accuracy rates that astonished the engineers who had designed the specifications. The numbers are the story. They always are in American manufacturing. And these numbers are staggering. Before the war, the American watch industry produced approximately 10 million watch movements per year. This was considered a mature, stable industry operating at a comfortable capacity. The factories were humming, the workers were skilled, the supply chains were established. 10 million precision movements per year was the baseline, the measure of what American hands could do when working at precision tolerances in peacetime. The war demanded something entirely different. The war demanded not 10 million precision components, but hundreds of millions. The Norden bombsight program alone required the production of over 170 million precision parts, 90,000 bombsights times 2,000 parts each. The proximity fuse program required 22 million complete assemblies, each containing dozens of precision components, miniature vacuum tubes, resistors, capacitors, oscillator coils, safety switches, and detonators, all assembled to tolerances that would have been considered extreme in any peacetime application. The military watch program, the A11 specification watches produced by Elgin, Waltham, and Bulova for the Army and Navy, produced millions of additional precision instruments, each one requiring a 15-joule hacking movement calibrated to lose or gain no more than 30 seconds per day. And then there were the components that nobody talks about, Artillery fuses, not the proximity type, but the conventional mechanical time fuses that preceded them, required clockwork mechanisms that were, functionally, miniature watches. Each fuse contained a mainspring, an escapement, a gear train, and a dial that could be set to a specific number of seconds. The fuse was a watch that you fired from a gun and that told time for exactly as long as you needed it to. 20 seconds, 30 seconds, 45 seconds, and then exploded. The tolerances were identical to watchmaking tolerances. The skills required were identical, and the quantities required were in the tens of millions. Bomb timers, navigation chronometers, aircraft altimeters that measured altitude by air pressure with an accuracy of 50 feet at 20,000, torpedo gyroscopes that kept a torpedo running straight and level during its journey to the target, gun directors on warships that tracked a moving aircraft and calculated the correct aiming point for the guns. Every one of these instruments contained precision gears, precision bearings, precision springs, and precision assemblies that could only be produced by workers trained in the traditions of the watchmaker's bench. The American precision manufacturing base expanded like a controlled explosion. Companies that had never made anything smaller than an automobile part were recruited into the supply chain. Subcontractors numbered in the thousands. Gear-cutting shops that had produced watch gears at a rate of a few thousand per week were asked to produce them at a rate of hundreds of thousands. The tooling had to be multiplied. The workers had to be trained. The inspection systems had to be scaled up from a watchmaker's loupe and a pair of calipers to dedicated measuring rooms with optical comparators and precision gauge blocks. The bottleneck was always the same: hands. Machines could cut gears, but a human being had to set up the machine, align the workpiece, inspect the finished part, and make the micro-adjustments that no machine of the 1940s could perform automatically. The final finishing of a precision gear, the lapping, the polishing, the deburring of edges too small to see without magnification, was handwork. It had always been handwork. And the hands that could do it were the hands that had been trained in the watch factories and instrument shops of Illinois, Massachusetts, Pennsylvania, and New York. By 1944, the American precision manufacturing base was producing military instruments at a rate that dwarfed anything the Axis powers could match. Germany had excellent precision manufacturing: the Carl Zeiss Optical Works, the A. Lange and Sonne Watch Factory, the instrument makers of the Black Forest. But these facilities were being systematically destroyed by the very instruments they were trying to compete with. The Pforzheim Watchmaking Center was annihilated in a single devastating raid in February 1945 that killed 17,000 people in 20 minutes and obliterated 80% of the city's buildings, including the watch factories and their irreplaceable machinery. Japan's precision manufacturing base was smaller, more concentrated, and increasingly cut off from the raw materials: the brass, the steel, the synthetic jewels, the specialty alloys that precision work required. The Americans, meanwhile, were untouchable. No bomb fell on Elgin, Illinois, no shell struck the Sylvania plant in Ipswich, Massachusetts, no submarine torpedoed a supply ship carrying ruby bearings from Lancaster, Pennsylvania. The watch factories and instrument shops of the American heartland operated around the clock, undisturbed, pouring out a river of precision components that fed every weapon system in the American arsenal. The ocean that separated America from the war zones was, for the precision manufacturing industry, not just a barrier against attack, it was a sanctuary. And the work that was done in that sanctuary, the gears cut, the fuses assembled, the watches calibrated, the bearings polished, was the invisible foundation on which the entire Allied war machine rested. The precision that came from the watchmaker's bench showed up on every front, in moments that most histories never record. The first combat use of the proximity fuse occurred on January 5, 1943, near Guadalcanal. Lieutenant Red Cochran, commanding the aft 5-inch battery on the light cruiser USS Helena, was tracking an incoming Japanese Val dive bomber. His gunners fired 3 salvos of proximity-fused shells. On the second salvo, the shell detonated as it passed near the aircraft, not on contact, not on a timer, but automatically, triggered by the tiny radio transmitter inside the fuse detecting the reflected signal from the aircraft's metal skin. The valve disintegrated. It was the first time in history that an anti-aircraft shell had destroyed an aircraft without scoring a direct hit. The miniature vacuum tube inside that fuse, assembled by a woman in a factory in Massachusetts or Ohio, tested on a circuit board, packed into a shell casing, loaded into a magazine, rammed into a breech, and fired at 20,000 Gs, had performed exactly as designed. The Navy was so impressed that it canceled the remainder of the testing schedule and immediately ordered mass production. By 1944, production had risen from 500 fuses per day to 40,000 per day. By war's end, 70,000 were being produced daily. The cost per fuse fell from over $700 to $18 as production scaled. 22 million were built in total. On D-Day, June 6, 1944, the A-11 military watches issued to American troops were synchronized to the second. The hacking movement, the feature that allowed the second hand to be stopped by pulling out the crown, enabling precise synchronization, was a watchmaking innovation that became a military necessity. When the paratroopers of the 82nd and 101st Airborne Divisions jumped into the darkness over Normandy, their A-11 watches were all reading the same time, to the second. The naval bombardment, the airstrikes, the beach landings, the glider insertions, every element of the most complex military operation in history was coordinated by watches built in the factories of Elgin, Waltham, and Bulova. At sea, the proximity fuse transformed naval warfare in the Pacific. Kamikaze attacks, which began in earnest in late 1944, presented a threat that conventional anti-aircraft fire could not reliably counter. A pilot deliberately diving his aircraft into a ship at 300 miles per hour gave the gunners seconds to react. Time-fused shells required the gunners to estimate the range and set the fuse before firing, a process that consumed precious seconds and was wrong more often than it was right. The proximity fuse eliminated the guessing. The shell simply had to pass near the aircraft. The tiny radio did the rest. In the final year of the Pacific War, proximity-fused anti-aircraft fire was credited with more than half of all Japanese aircraft shot down by naval gunfire, even though only 25% of the shells fired were equipped with VT fuses. The mathematics were stark. A proximity-fused 5-inch shell required roughly 300 rounds to achieve a kill against a kamikaze. A conventionally fused shell required over 1,000. The difference was measured in ships saved, in sailors alive, in a fleet that survived to support the invasion of Okinawa and the final assault on the Japanese home islands. In December 1944, during the Battle of the Bulge, the ban on using proximity fuses over land was finally lifted. Artillery shells equipped with VT fuses detonated overhead, spraying shrapnel downward onto German troops in their foxholes and trenches. There was no protection. A conventional artillery shell that landed 10 feet from a foxhole might leave the men inside shaken but alive. A proximity-fused shell that passed over the same foxhole detonated in the air above it, and the shrapnel came down like rain. General Patton credited the proximity fuse with helping turn the tide of the battle. The fuses had been so secret that their use over land had been prohibited for years, for fear that a dud might be recovered and reverse-engineered. When the crisis of the Bulge made the risk acceptable, the weapon that the watchmakers had built was unleashed with devastating effect. Germany had watchmakers. Germany had some of the finest precision engineers on Earth. The Carl Zeiss Optical Works in Jena produced lenses that were the envy of every allied optical manufacturer. A. Lange and Zona in Glashütte made watches of extraordinary refinement. The Black Forest clock-making tradition stretched back centuries. But Germany could not scale its precision manufacturing to match American production volumes because its factories were being destroyed by American bombs guided by instruments made in American watch factories. The circular logic of precision warfare, the watchmaker builds the bomb sight that guides the bomb that destroys the enemy's watchmaker, was a loop that favored the nation whose factories were beyond the reach of enemy bombers. American precision manufacturing operated in sanctuary. German precision manufacturing operated under siege. Japan had even less. Japanese precision manufacturing, though capable of producing individual instruments of high quality, lacked the depth of industrial infrastructure to mass-produce precision components in the quantities that modern warfare demanded. Japan attempted to copy captured American instruments, including Norden bomb sights recovered from downed B-25s, and found them too complex to reproduce at scale. The same manufacturing culture that had produced exquisite swords and delicate ceramics for centuries could not, in the compressed timeline of wartime, build the industrial base needed to mass-produce mechanical computers and proximity fuses. The precision gap was one of the great asymmetries of the war. It does not appear in most histories because it is invisible. You cannot photograph a gear tolerance. You cannot film a bearing surface. The precision advantage shows up only in the outcomes, in the shells that detonate at the right altitude, in the bombs that fall on the factory instead of the field, in the watches that keep every soldier in the invasion synchronized to the same second. The American watch industry won the war and lost itself. When the conflict ended and the factories converted back to civilian production, the companies discovered that the world had changed. During the 4 years that Elgin, Waltham, Hamilton, and Bulova had been making fuses and chronometers and altimeters, the Swiss watch industry, neutral, unbombed, uninterrupted, had continued exporting to the American market. Swiss brands like Rolex, Omega, and Longines had established distribution networks, built brand recognition, and captured market share that the American companies had voluntarily surrendered. The American companies tried to reclaim their position. They retooled, they advertised, they innovated. But the Swiss had a head start that could not be closed. The expression, running like a Swiss watch, entered the language, carrying an implication of precision that had, ironically, been exceeded by the American watch factories during the war. The women of Elgin and Waltham had built instruments of a precision that no Swiss factory matched in volume, but nobody knew because the work was classified, and by the time the secrets were revealed, the market had moved on. Elgin closed its factory in 1968. Waltham had already ceased American production. Hamilton shifted to Swiss movements. Bulova was eventually acquired by a Japanese company. The great American watch industry, the industry that had supplied the hands that won the war, died not from foreign competition alone, but from the ironic consequence of its own patriotism. It had stopped making watches to make weapons, and when it tried to make watches again, the customers had found someone else. The precision manufacturing skills that the watch industry brought to the war did not die with the watch companies. They migrated, they evolved. They became the invisible foundation beneath industries that most people never connect to the watchmaker's bench. The synthetic quartz crystal program, the 30 million crystals cut from Brazilian quartz that gave American radios their frequency stability, led directly to the development of synthetic quartz growth after the war. By the 1970s, synthetic quartz oscillators had replaced mechanical movements in most watches and had become the timekeeping mechanism in every computer, every phone, every microwave oven, every digital device on the planet. 10 billion quartz oscillators are manufactured every year. The technology that today synchronizes the entire digital world traces its lineage through the wartime crystal program to the watchmaker's understanding of how a vibrating element can keep time. The miniature vacuum tube technology developed for the proximity fuse led to advances in electronics miniaturization that paved the way for the transistor. The printed circuit boards used inside proximity fuses, one of the first mass production applications of printed circuit technology, became the standard method of assembling electronic circuits in the post-war era. The clean room assembly techniques developed for fuse production became the foundation of the semiconductor fabrication industry. The women who assembled proximity fuses in Ipswich, Massachusetts, were, in a very real sense, the spiritual ancestors of the technicians who assemble semiconductor chips in clean rooms today. The skills are different, the tools are different, the materials are different, but the fundamental requirement, the ability to work at scales invisible to the naked eye, with hands steady enough to manipulate objects too small to grasp, with patience enough to repeat the same micro-operation 10,000 times without error, is the same skill. The watchmaker skill, the skill that America developed in the 19th century, weaponized in the 20th, and digitized in the 21st. If you take apart your smartphone, you will not find a gear. You will not find a spring. You will not find a jewel bearing. The mechanical precision of the watchmaker has been replaced by the electronic precision of the chip designer. But the chip was made possible by the culture of precision that the watchmaker created. The conviction that a human hand, properly trained, could work at tolerances that seemed impossible, and that if you could do it once, you could teach 1,000 people to do it, and if 1,000 people could do it, you could arm a nation. Return, for a moment, to that room in the Elgin factory. The blacked-out windows, the armed guards, the women at their benches, loops strapped to their foreheads, tweezers in their hands, assembling devices they were forbidden to understand. They did not know they were building the third most important secret weapon of the war. They did not know that the tiny tubes they soldered would travel inside artillery shells, would be fired at 20,000 Gs, would spin at 25,000 revolutions per minute, would detonate in the air above a Japanese dive bomber or a German infantry position. They knew only that the work required precision, that precision required patience, and that patience was something they had learned long ago on the watchmaker's bench, fitting gears too small to cast a shadow into movements too intricate to comprehend without magnification. They were the invisible army. They wore no uniforms. They carried no weapons. They marched to no cadence except the rhythm of their own hands, steady, repetitive, precise. Hour after hour, shift after shift, year after year. And when the war ended, they went home, and the factories closed or converted back to civilian production, and the Swiss took over the watch market, and the women found other work or retired, and no one built a monument to the hands that had built the instruments that built the victory. 30 million precision gears, 22 million proximity fuses, 90,000 bomb sights, millions of watches, chronometers, altimeters, fuse timers, and jewel bearings, all of them produced by hands that had been trained to fit the escape wheel of a pocket watch, a wheel with teeth finer than a human hair, spinning 5 times per second, keeping time to within 30 seconds per day. Those hands are gone now. The factories are closed. The Elgin clock tower was torn down in 1966. The Waltham plant is a shopping center. The watch industry that produced those hands is a memory preserved in collector's cases and museum displays. But the precision those hands achieved, the 10,000ths of an inch, the mirror-polished bearing surfaces, the gears that meshed without play, the fuses that detonated within feet of their intended burst point, lives on in every guided missile, every surgical robot, every satellite, every device that depends on human beings having once learned to work at the boundary between the visible and the invisible. The watchmakers of Elgin and Waltham and Lancaster did not know they were building the foundation of the modern world. They thought they were building fuses and bomb sights and chronometers. They thought they were winning a war. They were right, but they were also doing something larger, something they could not see from their benches under the bright lights, squinting through their loops at gears too small to cast a shadow. They were teaching America to think small. And thinking small, it turned out, was the skill that won everything.